Hello, everybody from my side. So my name is Matthias Schubert. I'm a computer science professor from LMU Munich. And so the talk is called Surveilled Planet because I don't know if you know this Lonely Planet guidebooks. And basically during preparing the talk and looking at all the data sources, I don't think this planet is very lonely anymore because there's rarely a spot where you're actually really lonely today because everywhere has cameras and sensors. So it gives a huge point of data, which brings me to my main title, which is AI-driven Earth observation. So my usual problem of, okay. So first of all, because this is an ABINET talk, I felt like I first of all have to put some context to why does somebody from computer science working with Earth observation data is giving a talk in a group for energy transitions and sustainability. And I think information is crucial to any decision process. And so during my almost 10 years at ABINET now, I really witnessed that it is really a very complex problem. And a lot of the predictions we made were basically wrong because we didn't have certain kinds of information on the plan when we decided or discussed about what will happen in the future. So I think the most imminent thing was that I think in 2012, in my first summer school I attended, I wasn't even a full member then, we had this prediction that energy prices and fossil prices would rise over the next couple of years, and we had this very steep curve going on. And actually the whole opposite happened because Saudi Arabia decided it desperately needed cash, and it poured the market with cheap oil. And so economy in Alberta went down, but basically in the first summer school, no one of us had this on the schedule. So I think information is super important to make good decisions. And and this is mostly for the energy transitions about power plants, power lines, energy carriers, waste processing, storage. It's this whole life cycle Jules was discussing basically. And I think for surveilling all of these different effects, so it's very important to have good information. So there's always the theory and the plan, and then there's only what actually really happened. And this often deviates a lot because we just didn't recognize some important impact factor. So here's just some examples what would be interesting in this context. It's like the impact of climate change, land cover change, and basically I think like the remote sensors here, the geographers here would say, but that's our topics. That's right. So that's basically really I guess classical geographical topics where computer science is also interested in these because we are basically developing the tools for making good predictions here. So this is just a list of interesting topics. And so the interesting thing is that there's papers on these topics in both communities, actually. I'm not sure if everyone was aware about that. Okay. So how do we get this information? And it's also maybe more like a geographer's slide than a computer scientist slide. So in parts at least, so the first thing is, of course, sensor data. And so in general, I would differentiate between two types of sensors, which is mobile platforms like satellites, area vehicles, and maybe you even have a rover or something, but I think that's more uncommon if you not go to another planet. And then you have a lot of local sensors, weather station, traffic, parking, pollution sensors. So there's a lot of air pollution sensors, data sets around. So basically, I'm not actually the guy who makes the sensors, but I'm actually the one who downloads the data set afterwards and makes some prediction on these data. Okay, so we have online media, which is also something which we discussed in the beginning. And so basically in ABINET, it never came to some real work here. But interestingly, I saw some very interesting stuff, especially about Twitter, about the sentiment or about certain directions about how the fossil industry and how fracking is conceived. And so if you ask the right question, social media can be pretty insightful to see what people think. Of course, social media is biased and it's manipulated a lot. But on the other hand, we basically see that social media also had with this Cambridge Analytica scandal, it really has an impact on a significant amount of the society as well. So if you can influence 5% of the people in social media, this might decide an election or a referendum about leaving the European Union. So I guess this is like a noisy source of data, but it's an important one. And one other very interesting use case is basically that in the current crisis, so basically you can use, of course, military satellites, but you can also use TikTok and Instagram basically to see the progress of Russian troops, actually. And there was several photo series about like tanks at the border of the Ukraine right now, which basically are in position and which are basically posted on common social media like TikTok. Okay, and one last thing, and that's basically, I think, where like we're starting to talk more about why computer science is necessary is often we basically do not really observe what we want to know. So we have to somehow take the data, abstract the data, and the classical way how geographers do this is usually some kind of a physical model. So you have some physical laws and you can input some measurements into your formula, and then you derive like abstract knowledge. And basically on a similar track, but maybe with a little bit different capabilities here is predictive modeling. And so basically this is also something which might not be that new to geographers because there's geostatistics. So that's basically what statistics does, but machine learning is basically just another view on the foundations of machine learning as statistics, at least from my point of view. So that's basically like just, you do not really know what mechanics are in the data, but you basically have an observation. And if you have enough data, you can basically learn a prediction function even without 100% understanding what's happening there. And that's very valuable if you basically do not miss an impact factor, because the data has the advantage that it really like has all the impact factors in it because it's really observed. And whereas a model is basically you measure some measurements and then you predict everything that the model includes, but there's always like borders of a model. So some more words about the data we're using. So satellite data is actually more available now than ever, and there's a lot of nice. So I recently did some research about what's there on satellites for a project. We are actually like just a proposal we prepared with Jürgen and with Ralph. And at that point, I was just like wondering how many satellites are there. And then currently there's a list in Wikipedia that there's about 82 public domain or government agency satellites observing the Earth. So that's not for transmission of television. It's really like Earth observation satellites. And you can see this down here. That's some poster I found interestingly at NASA about ESA. So it's an American poster about European missions about Earth observations. And then you can see here that the different satellites which are there and which regularly still offer imagery or sensor data about the Earth. And these platforms vary in instruments. So that's basically from the visual spectrum to shortwave infrared, radar. For example, radar is very important to make digital elevation models. Then they're basically different in the coverage. So how much area on the Earth do they really cover? And the resolution. And resolution can be distinguished between like a temporal, in my opinion, it's kind of a temporal resolution and a spatial resolution. So the spatial resolution is what I have here on the slide. It's basically like what area on the Earth surface is covered by a pixel or by a pixel in or like a point in your raster data. And the second aspect is basically like how often does a satellite cross in certain area. So depending on what you want to do, that's basically very important. So if you just want to measure the elevation profile, then you don't have to go over every area very often. But if you really want to see changes, I don't know, like in vegetation and so on, if you want to track impacts of natural catastrophes, then it's basically very important that you have timely information. And then it comes in very handy that there is a lot of different that there's a lot of different satellites going there, because like you can basically check for the next satellite crossing over the area and do not have to fixate on one particular one. Okay, so there's example products. So I can imagine that other people know much more, but these are the ones which I was really concerned with. So that's digital elevation models. We will see later on for why they are generally even useful if just analyzing ordinary RGB imagery. And so we have this use case about like, what can you do to detect heavy methane emissions? And there's also like a couple of nice methods out there. And then there's aerial vehicles. So we can distinguish between unmanned aerial vehicles and manned aerial vehicles. So the major difference is that if you use drones, it's usually much cheaper. It's not so, your coverage is lower, your resolution is higher, and the imagery you're basically generating has much more perspective. And on that I will elaborate later on. That's an important difference between if you have satellite or drone imagery. And then you have manned aerial vehicles, more expensive. You basically can carry larger sensors. So this plane here is not actually like a camera, but this is a LiDAR sensor, which really makes 3D point clouds. And so there, basically, I know that Craig and Julia and Guillermo for the Bearer project had something like this in action for the project to get point clouds of the complete study area. Okay, so let's go a little bit more into the details. So basically, if you get a raw image, it's a video. So it's basically you have frames, or you have a couple of frames together. And you can see this here on the right-hand side. This is from a data set from somebody who just like published on GitHub a drone data set. And you can basically see that it goes from the lower hand here up. Let's maybe switch on my pointer. Just a second. So you can basically see that this is the first frame, and then basically the drone flew along this street here, and you can see trees, cars, and building getting here. And so in general, like what is done next is usually something called auto-rectification, which basically like pins this imagery on top of the Earth surface, so it can be compared to other local measurements you're having. And then what's usually also done is you're not sticking with the video, but then you basically patch these video together into something called an orthomosaic, which you can see down here. And so this is basically a joint raster image. And so I'm elaborating on this, even so most of you might already know, because this has impact on the image quality. And so I just want to explain this shortly here. So the auto-rectification basically works in the way, or like the problem with it is that it's depending on the elevation profile of the area you're photographing. So the yellow boxes you see here is something from maybe tracked from a satellite, which is a digital elevation model. So it's basically the measurement of what is the elevation on this area. And so this brown line here depicts like this is the real elevation of the surface. And so that's basically different because like we have raster data here. So you have like, I think like for the cheap ones, you have 90 to 90 squares. Like I think today public might go down to 10 to 10 meters. But depending on how close you are, this is also not really exact, okay? So what basically happens now for geo-rectification is that if you walk along this ray, you basically see, okay, like the true point on the Earth surface of this pixel you would record up here would be the green line. And then basically, if you just correct it with the digital elevation model, you have the red point. And if you don't do if you don't use auto-rectification, you would basically end up here. So you can see there's a large discrepancy between the area or like the location of a pixel without auto-rectification with auto-rectification. Okay, so that's one effect we're having here. So take away what's important later on is that basically like the camera position when an image has been recorded plays a role about like how it is pinned to the Earth surface and how the geo-coordinates are. And that's not an exact process. So it's pretty good, but it's not 100% exact. And depending on the quality of the data you're having, this generates a lot of artifacts and noise. And the second problem we're having is if you have like orthomosaics, and this is especially if you go down from satellite imagery to this mobile platforms like drones. And this is basically the impact of perspective. So if you pin together an orthomosaic, what you want to have is something like an ambivalent camera. So it's basically you want to see everything, as in this case here, like your camera is on top of the object, and then it goes down from perpendicular angle basically to the Earth surface. So we basically just the top of the object. But if you have like drone imagery or airplane imagery, what you have is basically more like this. So you might have some area where we really have this kind of picture, but if it's off the axis a little bit, then you might get something like this. And we will see that later on, see this perspective. So you basically see the object from the side. And this effect gets stronger the closer the camera gets to the ground, obviously. Because if I move up infinitely large, I have basically this ambivalent camera, which sees everything on top. So in satellite images, this effect is not so bad. But like if you go down with a lower flight altitude, you will see that the imagery basically has much more perspective in it. And this also might cause noise. And so I'm insisting on this because that's basically part of the research, how to cope with this noise, which happens here. Okay, so finally, just some words are already motivated about AI and physical models. So, so in general, like I think we had a lot of discussions about how physical models and AI over the last couple of years would fit together. And I think in the beginning, I was basically, when I first arrived at Avinet, I was asked that nobody needs AI, everything can be done in physical models. And then we had this discussion. And during the last couple of years, especially when I started to work in neural networks, I more and more saw that that's not, in the paradigm, it's super similar. It's not really that different. So the approach is a little bit from different ends. So like in a physical model, you apply physical laws, which are justified, which you basically know, which hold in a controlled environment, and then you transfer to the real world. And in most cases, then you things you're doing, at least with the effects you're measuring, are pretty good, and you can already exploit this. And so in a way, like if you can use a physical model and it works out, so you don't need to have any empirical model fitted, because yeah, it's basically like you have shown that these models actually really make sense. But in a way, like if you think about how these laws were developed, it's also like somebody wrote up some formula and said it made sense, and then basically started to do experiments. And so the whole area of experimental physics is about giving empirical evidence that these laws really hold, right? So maybe not so different from the empirical method. Okay, so AI starts more at or machine learning. So basically today, AI and machine learning is merged into one. So I apologize to all general AI people. So AI usually is much more than machine learning. But like in common speech, everybody now just speaks of AI. So it's like a much larger area. It's not just machine learning. But the machine learning view is basically you observe empirical data, try to build functional predictors, which generalize to new cases. So in the ideal world, like if we have enough cases, we basically, if we would do it in the controlled environment, we would find those physical laws again. And there's already some papers from DeepMind where they basically have neural networks which basically learn physical laws from a controlled environment, actually. So you can argue how useful that is, but it basically shows that if you have enough data, if you generate the right environment, then basically you can find the laws, the same function empirically that you basically like derived manually like years ago. Okay, so in the real world, both methods have their shortcomings. So I start off more like with if you just apply the laws, and yeah, if observations are not directly observable, missing or noisy, that's something which you somehow have to integrate into your modeling. So I don't claim that there is no method to do that, but it's basically not that you can just open up your school book of physical laws and completely apply it. Yeah, so I think one of Ralph for the interdisciplinary approach is that like in the models people do, you always have this border where some impact factors are not really considered. And then this makes this strange behaviors we might not be able to predict. And so basically integrating more knowledge, which might not even be like on the same type of data, that's something which is valuable, because it could basically tell us why the models do not really predict what's happening, or maybe like just how we can improve them. And then also a factor about using physical laws is basically the granularity. So often, and this also holds in the area of reinforcement learning, like if you do train an agent on an exact model, the problem is sometimes really like if you basically could handle the complete model and all its details, then you basically would have a nice solution, but it's usually too expensive to compute. And so basically just estimating a distribution and not like really like going into every detail case helps a lot to make problems like feasible in the first place. Yeah, sometimes you basically do not really know how physical models for a particular task works. For example, like if you want to give a physical model about what is a tree, I guess that's pretty hard to define. Yeah, but in general, like, so you could basically maybe find some super complex formula which could detect any tree from a color spectrum. And so you would have a physical description of the image a tree would generate, or the reflection of a tree. But that's basically, yeah, like connected to a lot of different varieties, distributions, and so on. So basically nobody would do this manually. On the other hand, functional predictors are also not perfect. They rely on significant samples and distribution processes, which makes them basically not suitable for a lot of problems which are tried. For example, like if I want to simulate climate, it's maybe not so useful because actually I don't have empirical data what in a similar situation happened on other planets. So I don't have 1,000 planets where I can basically see, okay, like how did climate change work out there? And so on this scale, it's not really helpful. And so generally another problem, which we also discussed, is it might model the observation, but not the relevant latent factors. And this is basically this causality, this debate we already had. So it's basically, we observe something, we have proxies, we can observe correlation, but we basically do not really track the reasons behind it. And this makes these models a little bit, yeah, like it can be attacked just by simply like changing the impacts, but not basically the reasons. And then this makes it also, it limits a lot the transferability of a model to a new situation. Okay, so just some final words about these two kinds of approaches. So actually there are already works, and I think physics people are super interested right now into neural networks, and they already start doing works and integrating both. And in general, it's not so complex because basically physical laws and neural networks are just mathematical formulas on a certain syntactic level. So integrating them, it's not so complicated because you can either fit a neural network into your formula or the other way around. You can basically like just say, okay, like I know that these features transform into this by applying this physical law, and then can just use this as a pre-processing step or a step within the network. So that's something, and there's already first works on this. So just Google took the first one, is fusing physics-based and deep learning models for prognostic reliability. And so basically, this was just like the first thing which popped up, but you can already see that there's already some fusion going on here between like physical models and deep learning. And I think it's largely driven by the physics community. Okay, so for the next 3 slides, I will give you a super brief introduction to what deep learning does. And so it will be super flat. So the first thing, what is a neural network? And a neural network is an universal function approximator. So that's basically, it's just a framework where you can, yeah, like model any kind of function, and it's super flexible. It can go to billions of parameters. If you think about the architectures people using for modeling the English language. So you might have heard about BERT or GPT-3, which is in use in the web interfaces right now a lot. But in general, it's all like the structure is you have some input X, which is the observation. You have your output predictions, which I picked it here with this Y, and you have theta, which are the function parameters. And so the trick is now that you basically input the data and check whether like what you input basically has the right output. So you basically want to optimize the parameter theta so that the output for the input X is like you want it to be. And this what like you want it to be might be described in a different way, and that's different tricks. So the most common one is supervised learning, which is basically, okay, you give examples of this is the input, this is the output, and find the parameter setting where you basically have in most cases, a fitting output, which is close to the true targets you're having. And so this is also known as classification or regression. Okay, so then you have unsupervised things where you basically do not have example what should come out, but what you can do is to say, okay, like the output should have some structure. So for clustering, for example, you just say, okay, like if I find an output which tells me like there's 10 groups of objects which are very similar in there, then I have found a good model. So a little bit newer approaches are self-supervised and adversarial learning. So for self-supervised learning, the idea is basically that I can generate two versions of the same input. And usually this is done with images. So what I can do is I can flip the image, I can rotate the image, I can change, color parameters and so on. I can basically take just a patch from the image and so on. So basically I somehow modify the image, but I modify it in a way that the object on the image is still the same. And I could also use basically two pictures of the same objects, which are taken from a different angle or something like that. So that's all possible. But usually what you do is this kind of image augmentation. Now the idea is that I found a good model of my data if I feed in these different versions of my object, but I always still get the same result because it's always a dog. And so that's basically some trick where you can remove irrelevant parameters and just focus on what's basically on there. And the nice thing is that you don't really have to have any ground truths for training. Okay, and the last thing I just want to mention, because you might have heard this before, that is adversarial learning. And this is some kind of tricky because you're using a second model, which basically learns to distinguish the wanted output from the output of the network. And basically the trick is here that the way it is trained, like the signals from the second classifier can be directly used to modify the parameters of our function approximator we actually want to train. Okay, so one final word is various methods are available. So this is not complete, but what's important here is that we neural networks usually find good parameter settings, and that was one big point of criticism when neural networks was rediscovered basically, because for some times nobody cared about them because it's just a good parameter setting, and this means like we have good results, we have better results than before, but we cannot guarantee that this parameter setting is optimal. Okay, so some words about evaluation. So one thing what we also have to keep in mind, no matter how we are training, you always have to have some ground truths about results we're having just to justify that what our network did is the right thing. So we always need to have cases where we have the proper output for an input just to check, did the neural network learn anything? And what's also important is that we shouldn't use, basically we are not allowed to use the same pairs of input and output for training the neural network, so for optimizing the parameter theta, and for evaluating, because what we have them is this overfitting effect. And overfitting is basically like if you remember, basically if you think about a child learning to calculate something. So what you can either do is like you can teach him okay, 2 times 2 is 4 and 3 times 3 is 9 and so on. But basically this, if you just like go through this table, your kid won't learn basically what is 3 times 4 because it doesn't really learn to multiply it. What it basically learns is that this combination of inputs generates this output, but there's no knowledge behind it. And the goal of machine learning is really like to find this implicit laws where you can, where this network can start to abstract to new cases. And that's why it's super important always to confront the network with a new case, so it can basically show how it can abstract to the new problem, because otherwise it will just learn to reproduce what you just talking, and then it's basically nothing else than a database. So it's just like, for this input output, do this. But that's basically not helpful because like for the training data we know anyway, and if you cannot apply it to new data, it's useless. Okay, so some words. So the network architecture is basically the exact specification how this prediction function f looks like. And usually this function is constructed in so-called layers. So we have the first layer, which is a function, and then we take the output of this function and wrap around another function. And then we take another function and another function and another function. Each of them has parameters. And that's basically what people refer to as layers. So one very important thing, and this is maybe why deep learning is really built on the neural network paradigm, is that the only requirement we have for optimizing our parameters here is that these layers are differentiable. And then we can use the chain rule. And this means basically if we stack up these functions and each of them is differentiable, it means like the whole function is differentiable. And then we can use gradient descent and variance to basically optimize it. So gradient descent has one big advantage. So it basically just has this requirement that the universal function approximator is just differentiable. And you can even like tweak it a little bit that it doesn't even have to be completely. But on the other hand, it suffers from some implicit problems, which means like if I have too many layers, then gradients will just disappear and it won't optimize anything. And so this is effect called vanishing gradients or exploding gradients. So anyway, in theory it works, in practice it's a little bit more difficult. So the conclusion is that basically any differential function works this way, but in practice, usually it won't, because you will have the requirement to have too much data. You basically will have too much steps because the parameters at lower levels are simply not reached in a way and modified in the way they should be to have things. So the whole area of deep learning is now about like finding these building blocks. I just sampled some of them, which basically allow you to still optimize all of the parameters, even if the model is huge. And so these are basically these Fs I just had in the stacking. So these are the typical layers we're having. So, so the first one, which is the most well-known one, is a linear layer. But the linear layer suffers from all of these problems I just told you. So this is like the traditional neural network you're having, and linear layers have kind of, if you have the same number of internal nodes than outputs nodes. So basically your first function has the same number of output variables and the input, and you have this quadratic size of parameters. And you can imagine like if you feed some image into it, so if image has always like the number of colors, so maybe like RGB, 3 channels, but then you have heights times width. And so you have this cubic complexity of the input. So you can imagine that if you square this even more, like the number of parameters is horrible. So most of the newer architectures use some linear layers, but you have to use linear layers pretty sparsely because they really have a huge amount of parameters. So what was one of the first successes of deep learning is the so-called convolutional layer. And so the convolutional layer is just highlighted here. So what you basically have, and this is applied on a pixel image, you have this kind of a local area you push over the pixel image, and then you have some kind of trainable filters here. So you basically apply the same set of filters on any pixel environment, and then you just have as an input, you have all the channels here, and this limits a lot the number of parameters. And stacking these type of layers was super successful. This is basically, I guess, one of the first big success stories of deep learning where it basically worked. And so the trick is really like using these convolutional layers, which dramatically reduces the amount of parameters and simply exploits it on an image that you basically have this hierarchical structure that you always like summarize close by pixels. And if you stack this several times, then you can really distinguish a lot of different things. Then you have like this recurrent neural network. So this is just like this is from a German guy, or like basically one German and one Austrian guy, so of Hofreiter and Schmidhuber. This is called a long short-term memory. But a recurrent neural network is basically a network where you feed in a sequence, might be temporal or just anything, and it just tries to memorize stuff along the sequence, what's necessary to predict the next stuff or to predict something. So this is so basically for all kind of temporal sequential data, this recurrent neural networks, GRU, LSTMs are very important. And down here, this is basically the last big success story, so-called self-attention layers, which are basically a way to do the same thing as a linear layer, but a little bit more clever. And so this reduces also parameters. It still has a lot, but if you think about all these modern language models people were talking about, which can write essays and so on, they're basically built on these building blocks. For imagery, what we talk today, there are some larger architecture blocks like pre-trained images, and I just have as example this ResNet V101. And what you do here, that's basically, you see here that there's convolutional layers in here. You have some additional building blocks like batch normalization and rectified linear units. And what you also have here is something called a skip connection. And this is basically the idea that you make shortcuts between the layers. And this is mostly useful because this allows gradients in the training to directly go down to the lower layers. Yeah, but I really try to keep this short. So basically, takeaway here is like deep learning is depending on the building blocks you're using and how you cleverly combine them. And so there's a lot of libraries right now. And so if you combine these blocks, you can train them by gradient descent and variance. Okay, so what is there on further tasks for deep learning on raster data? So the first thing we already had on the first slide was this classification or regression. So this basically means that we feed in some piece of raster data and then we got some numerical or categorical output. Usually that's not too interesting. The second thing, which is a little bit more interesting, and that's what I was working with a lot, so that's why these are all example images from myself, is object detection, which basically says, okay, we want to find a certain pattern on the data, like the planes here on this airfield or the cars here on the street. Or this is actually from the paper with Craig, Giuliano, and Michael. This is basically from like detecting the seedlings and the seismic line. Okay. And the last thing, what is done, which may be like the most difficult discipline, is the segmentation. And for segmentation, we differentiate between 3 types. So we have instance segmentation, semantic segmentation, and panoptic segmentation. And what you can see here is semantic segmentation, which basically tells you we want to have the pixel which shows the same thing. So we have building, people, cars, and so on, but we cannot distinguish the cars. And instance segmentation basically finds the different cars, which is basically combined with some kind of object detector. So the common way to do instance segmentation is first detect the objects and then segment what pixels do belong to the object. And there's a combination called panoptic segmentation, which basically does both. So it basically segments all the pixels on the image without detecting them first, but also is able to distinguish different kind of objects of the same type. And so there's first works on this panoptic segmentation as well. So finally, some words about like what problems are there on Earth observation data, which I basically worked on to help overcome, which are specific in this area. And so the first thing is usually there's always limited or spatial temporal resolution. And so because like it's always like if you have a certain resolution, then you might always be interested in a pattern which is not covered very well in this distribution. And this is some example from Sentinel data 20 to 20. What you can do here nicely is like you can maybe like see that there's a buildings here, but like for cars this would be kind of difficult. And of course, you have recording conditions, which also make your life more difficult. So you basically cannot use any satellite image, for example, because cloud cover plays a major role. And so a lot of these measurements I just had in the beginning are very difficult to use if the cloud cover is too strong. So basically, if you go to a portal downloading satellite imagery, will always have like this percentage, even in the selection mask, how much cloud cover is there, because this strongly limits your usefulness in many areas. Illumination is a problem. It might not really be a problem the way that you don't see anything, but images, if you have a different season of the year and you go to the same area, like, and if you make a 5 o'clock, you make a picture, then it simply looks different because the sun is completely in a different area. And then haziness is also a problem. So if you take Earth observation imagery, you always have to consider that this is outside. And so nature, weather condition play a major role in how good your measurement is. Might be even that if it's windy, that it's much harder for a plane or a drone basically to stay calm to make a picture. And if it's dark, then it's also your imagery will be more noisy. Okay, so one thing I think which is not so aware is like the ground truth is always image specific, and then generally it's sparse. So I think sparse is quite common because ground truth usually is generated by people. This means like somebody has to sit there in front of the imagery and draw polygons, mark pixels, draw boxes. And basically nobody wants to do that. So you can pay people with Amazon Mechanical Turk, but that's usually because people are paid, but they don't still like it, so the quality is also not too high. And so depending on how good the people are, and basically it's all like, even if you did it yourself, you know basically that your quality of labeling is not very consistent. So ground truth generated by people is not like the real thing. That's also some kind of it's basically a good detector, but it's still error prone. And usually it's always sparse because people do not want to do it. And in geodata, it's especially complicated because like if you basically just want to detect cars or cats or anything, you can just use reCAPTCHA and can force people in the internet to do your labeling. But like if you want to have specific signals, which not everybody can basically understand, then it's basically you cannot just go to a broad public and try to force them to do your labeling. And a second thing, which is basically dependent on these two effects about like imagery we're having, is that like the fit of the annotation is really usually specific to the image. And so we had some discussion here to use geolocations as annotations. And so like to take about the last paper I'm going to talk about today, it's possible to use, but it's not straightforward. And one last thing is the robustness of models. And this might depend on how the recording is there. And this basically depends, like if you train some kind of a detector on a certain type of imagery, it's not per se not directly applicable to any thing of the same problem. So in this area, like for example, with our seedlings, we made some experiments that like if you do not really like cover different areas and different seasons, and this is just an example from this paper I mentioned as well. It's the same patch with respect to the area. But you can see that the one thing is about 2 months after. I think the one thing is in October, and the other thing was the other picture, like the on-leaf period was in August or July or something. So correct me if I'm wrong. Okay, finally, yeah, so finally, I see that I'm already, okay, so I will try to keep this in mind. So yeah, so I just want to mention some of my own work or like my PhD's work. So this first thing I just want to introduce is how we can use neural networks for spatial interpolation problems. And so the idea here is that basically measurement stations here are like point measurements. But if you want to know things like temperature, humidity on a different area, then we need to find some interpolation method to say, okay, what is the area there? And so the use cases was driven by depicted on the right-hand side. So what we had here was like weather stations in the mountain. And we basically wanted to have an idea about the temperature on any area on these mountains. And so what deemed to us, it was very important to not just take spatial distance into account for the interpolation, but some kind of elevation profile, for example. And so what we basically did was we modeled this whole problem as a graph neural network problem. And so that's basically the graph we're having here. So we have measuring stations. And so the way it works is basically like these are the stations where we have the measurements, and these one are where we don't have the measurement. And what you can see here is that we have some different messages passing from the stations to each other. And you can even see that we have this message passing even to the nodes where we know the stations. And but this is basically to learn how this is connected. And so there's statistical methods for this, which are similar. But the nice thing is basically that we can now learn which messages are passed from one node to each other based on different parameters we're having here. For example, the elevation. Or we could use other things. So for example, I always wanted to apply, but I never found a data set this for pollution data in a city and see like how many buildings are in between the measurements. Like how's the wind, for example. That might be also some reason. So the nice thing about the framework is it's generally applicable to all of these different impact factors by just like learning how these impact factors should impact these messages we're sending around. And from there on, it's basically just the same approach again. So we did some experiments here and compared it to things you might know. So there's the baselines like K and N and it was distance weighting, and then we used statistical methods like p-kriging and kriging. And then we had some simple neural network just to show that it's not easy to just feed everything neural network and it does fine, it does not. So you can see that this is performing pretty worse. But what you can see is that these are our models, and this is one with the elevation models, and it's slightly better than the p-kriging here. And the same for the humidity. And so this was for a data set where we have like 233 stations. And this is just like 10% of these stations were like about 23 stations were basically for training, and we did the prediction for the rest. And you can still see that it's pretty close to what's state of the art. So it's a little bit better. So there's variation is a little bit higher here. So, but it was quite comparable here. But the nice thing about the approach is I don't think it's really like the comparing to the kriging, but it's really like the way that you're basically free to integrate temporal data and different kind of impact factors into this interpolation process. Okay, so the second paper is actually like first authors are Nianchan Ray and Zakaria Ravi, which are actually from U of A, so it's more like a Canadian work, and I was just like co-supervising Zakaria's master thesis. And so this end-to-end super resolution and object detection. So that's yeah. So the idea here is that you usually have like this limited resolution, or often have, so if you want to use satellite data, for example, usually for smaller patterns, your resolution is not high enough. But you sometimes have, for a limited area, you have this high resolution imagery. So what's out there is this so-called super resolution networks, which basically can scale up algorithmically, but just by learning how this low resolution impact would look like if it would be high resolution. And then you can learn this network, which transfer a low resolution image to a high resolution network, and then directly apply the object detector on it. And the idea of this paper was basically, can we basically take the error of the object detector to optimize the super resolution? So in the end, what we get is basically a network which gets a low resolution impact, low resolution image as an input. As an output, we get object detection on a high resolution image. And so that's the architecture. Just a short walkthrough. So basically, this is the super resolution network. So it's basically like receiving a low resolution image. It scales up the image with some convolutional layers and some tricks here. So we had this additional trick here that we had a edge detector here. So this has some edge enhancement in this area here. And so what we had here is basically this error, which basically checked like if this artificially scaled up image looks like a true high resolution image. And then we have on top of here the feature detector, which is basically detecting if where the objects are. Okay, so if you have questions, then I can answer them later on a little more detail. So maybe what's more interesting is what does this work out? So this is just an example we're having here. This is a car data set, and what you can see here is this is a low resolution image scaled up. So that's why it's blurry to the size of the high resolution image. And what you can see is like if you apply the super resolution, we can detect these two cars here, which are not being detected on this image here. And there's a second data set about fuel tanks on a bunch of drilling sites. And you can also see that basically, like if you work on the low resolution data, like the system would have just distinguished 3 tanks, but after super resolution, we found 4 tanks. And this is basically the lines about the average precision we receive with the blue line with the super resolution and the red line without super resolution on both data sets for different recall levels here. Okay, so you can see basically that this one goes better. Basically, this one up here, this would be the optimal detection rate. So we detect everything with 100% precision, no false positives, no false negatives. So the closer the line gets to this point here, the better it is. Okay, and you can see basically that for this data set, we did improve, but maybe not so strong. But for the car data set here, that's basically like a very strong improvement, because the whole area here is basically an improvement. So here's some further pictures. So how does it work? So, so this is the original image in the original size. This is just by scaling it up. So you can see that it's kind of blurry. This is after the super resolution. I think that's kind of nice to see it right behind to each other. You can basically see what the network does, how it sharpens the edges here, and the cars are much easier to detect. And then basically we can apply the detection. And this is basically all the original image on the high resolution. We compared it here. So in this case, you basically artificially generate the low resolution imagery by just removing input samples. Okay, so here's some additional samples here where you can basically see that the scaling up works pretty well. And yeah, this brings me to my last work I want to present today. And this is basically why I described so well where errors in geo-rectification come from. And so I think that's a very interesting work because it basically, the idea came up when we were working with Giuliano and Craig and Julia on this Edmonton tree project. And so the problem is that if we use a neural network for an object detection, you usually require precise annotation boxes for training. And we tested this, and if the boxes are noisy, it basically does not really work well. So you have large losses in the detection rate. Yeah, so annotations are generally image specific, which means like we have to label them manually. And basically we had this idea that or like when I asked for labels, say, the geographers in the group just came over and gave me some ArcGIS layers, basically some polygon layers, which in practice would be very good even for segmentation. But when we looked at them, we found out, okay, it's maybe a little bit difficult here. I like to exactly fit it here. And there are some errors, and then we did some research where the errors come from. And the errors basically really come from making orthomosaics, orthorectification perspective. And so I will have just some motivation example on this data set in the next slide. So the idea is basically, can we basically take the data we have from geolocations? So like, can we directly take point annotations and generate labels we can use to train an exact object detector on it? And that's basically what we did in this work. So we basically took data, took a close by geo position of the object we wanted to detect and tried to build a label box from this object where we had this point supervision. And so this is some motivation from this Edmonton tree data set. So what you can see here, basically, like these points are the same. This is from the GIS. So that's basically the same points we're having here. And you can see that's different days of recording. I think it's even like 2 years apart. And what you can see here and different times of the year. So the tree here looks much different than the tree here. And what you also might recognize is that the point here is a little bit more away from the path than up here. But it's the same GPS point. So I just generated these images by just removing one raster layer and just like blending in the other one. And what you can see is that you have these deviations here because the points you have here, and then basically I just manually like attached these bounding boxes here. And you can see also that the position of the GPS point where the tree is actually was measured, and the actual bounding box is also different. But the nice thing is basically the point is still in the box, right? So the idea was now like, can we build a nice box out of these points? And the good answer was, in most cases, we came up with a very nice method to do that. And so that's the architecture. So it uses also, like I described in this adversarial case, 2 versions of the same image. But what it basically does is it takes a point, it generates an environment called the Gaussian blur. So we just make a Gauss distribution on top of it and mark close by pixels to also be relevant. And so we use these pixels as supervision. And then we try to train CNN based on this input image to predict the pixels which are blurred. And to get this more stable, we generate 2 versions of the same image and basically use the annotation we got from one image as supervision for the other one. That's why we have this crossing here. And then we have an additional algorithm which basically tries to improve the position, the center position of the object. And so in this base, like after this architecture you see here, then we basically have corrected object centers. And in the next step, what we do is basically we take these centers and say, okay, like we start off with an estimated box size for this type of object, and then we basically adjust it using this class activation map that's depicted down here. So this is the class activation map from the previous step, which is basically the output of our network telling us like how likely does this pixel belong to a particular class. And then we can build a bounding box here, and then basically, since it worked better if we have some basic size and some bias on the actual size of the object, and then we basically adjust the predefined fixed size object towards what we had in the class activation map. And by the way, this is a real image. So that the object here is this kind of a harbor object here, and then basically we have like these three areas where the boats are. And then like also basically what we show here is that these are other methods which were generated for noisy data, and like you can see here that this is mean average precision. So like the best thing on this is a car data set. That is a data set on palm trees. I will show some example on the next slide, and this is for general objects like sports fields, harbors, bridges, and so on. And so what you can see here that using our correction method in combination with faster RCNN or RetinalNet, considerably improve the result compared to the other. And these two columns here have the same input. So that's basically noisy data, where we don't have this, we only have this point supervision, and the location of the objects were not really exact on top of the object. And you can see that this, for most of the objects, if you use a pure object detector like the first two columns, is basically half the accuracy you have if you have the exact. So the ground truths on RetinalNet and FAST, which are like the basic object detectors we used, are like about 96% if you have exact labels. But if you blur these things, then you have only 40%. So you're losing about 50% of your performance if you don't have exact labels. And that's again basically why this is important, because if you're using this not really well-fitting labels, then your object detector might not really be efficient or effective. And then there's like these three methods which also try to handle noisy data, but they do not do it in the same way as we did. And then we closing the gap. So we're also still losing about like 10% here. In this case, it's just like 4%. Here it's still pretty dramatic, but this has other reasons, because we have some problems we didn't really have coped with in the first catch. But like for these two data sets, it was pretty nice. So in general, like what worked well was the finding the object centers. So we are not so good right now in fitting the boxes. And since this is the only data set where we really have like a strong variance in the boxes, we performed not so good, but we still like had a 20% improvement. Okay, so here's some examples for what we did. So the red point is actually like the point level we got, and the green point is always like the center of the object we have, and then the box what we think is the object. And you can see here for this example here, so we can find the bridge even if the point was down here. So we can correct these images here. This data set is actually quite interesting, because we can see that there's a lot of objects with the cars, and we basically still make some mistakes, like with these two cars, which are not really well separated, but they're still much better than before. And so for the palm tree data set here, you can always see like we quite well find the center of the palm tree. And so it worked out in most of the cases pretty well. So, and then this is some problem we are also currently working on. Okay, so yeah, so I took a little more of my time than I should, but sorry for that. But so I'm finally at the conclusion. So, so first of all, just remembering Earth observation data can provide useful information to evaluate the impacts and predict future trends of technologies and what happens to climate and so on. So it's maybe not really like modeling or telling you what to do, but it can help you to understand what might happen or what's currently happening, or if something you tried out really worked out as planned. Okay, yeah, deep learning provides universal function predictors, which can be trained to a large variety of tasks and can be combined with physical modeling. if need be, and so it basically starts more like statistic on the empirical side and less on the known knowledge side. Okay, yeah, and deep learning can help. So sorry for the typo here, for integrating various information sources to improve prediction models, compensate low resolution measurements with super resolution, or generate pseudo labels if you basically just don't have really this manually tagged labels, but you have something else which also might help the network to understand what you're actually looking for. And yeah, so the last point I already mentioned, so that deep learning can complement physical models wherever enough empirical observations are available and exact physical contexts maybe are unknown. Okay, so thank you very much. And that's it from my side.